Thank you very much for that really awesome journey that I've had. Yes, so really appreciate the invitation to be here today. And I have to say, probably one of the best experiences of my life in terms of a car journey, as fantastic as a car journey can get, or rather in our case, a double-decker bus journey from Stockholm to Luleå, which is great. So appreciate the invitation, appreciate Jan Olaf and his team's really hard work and effort in making all this happen. I guess from my perspective, what I wanted to be able to do, there's a lot of detail in here, which a lot of work has been published out in the public literature. So lots and lots of information on the science. What I would love to be able to do is really give you a big picture overview of what is possible. The kinds of talks we've heard this morning from Göran and others really highlight the important question. You know, I mean, if we are going to achieve all the things that was mentioned this morning, the simple question is how are we going to get there? We need to be able to understand the science at the fundamental level. We need to be able to bring that into business, and we need to be mindful of the environmental and social implications of what we do. So I think putting all of that together, yes, it sounds very difficult, but the practical reality is that if you actually start to think about scientifically, do we have the ability and the capacity to do it? A short answer is yes. Not all the answers are available today, but certainly a lot of the answers are there in terms of the science. It's how we then translate that science and deliver the kinds of new economies, new solutions, innovation, and all of those things that we've been hearing about this morning. So, what's the role of the steel industry? One of the good things, I guess, with the steel sector has been our ability to be able to really push forward in terms of the very, very challenging conditions of high temperatures. The advantages of high temperatures are that you can actually look at the difficult materials. The difficult materials include things like plastics, glass, dyes, rubber, all kinds of things in all kinds of products that we use. So it's not just about, well, we're worried about steel and how do you actually recycle steel. Clearly, electric arc furnace does that. The question is, if you look at, for example, a car, and you sort of say, right, about 20% of the weight of the car is plastics and glass and all of these other materials. And if the EU directive, if I'm correct, says that you need to be able to recycle, for instance, 95% of the materials that come out of the car, obviously extended producer responsibilities apply to a whole range of other products. How do you actually achieve that? How do you make sure that all the different types of complicated materials that are actually present in cars, in our electronic devices, and the list goes on and on, how do you actually then get to the point where you can, in fact, in a sustainable manner, recycle and transform these types of products into higher value solutions? And that's really the core of the question here. You know, everyone wants to recycle. It's not that anyone says, oh, look, we're against recycling. Of course, societies want to do that. There are systems in place in many parts of the world that collect products. In Australia, for example, we've got government policies that actually look at how you might be able to collect end-of-life products. The question, of course, remains, why is it then that millions of tons of, for example, auto waste still end up in landfill? The realities are, as you will see in this talk, very complicated, different mixtures, different types of plastics, different dyes, different ceramic materials. And so the end game is that you cannot separate different types of plastics. You cannot separate different types of ceramic materials that are actually inherent in these mixtures. So the solutions have to recognize that separating and thinking about recycling in a very traditional manner, which is converting plastics into plastics and glass into glass, is really not going to be feasible. You cannot assume that just because you've got 10 different types of plastics in a car, you're going to separate all 10 of them out and create a whole new product. So this is where, of course, the nice thing is our understanding of high temperature reactions and what we can actually achieve at the most fundamental molecular level comes into play. If you actually start to ask the question, what are plastics actually made of? And why is it that the polymer industry is focused just on converting plastics into plastics? Sure, when you've got nice clean streams of plastics, for instance, it's easy enough to think about converting thermoplastics back into plastics again. or for that matter, glass back into glass again. The realities are, as we know in a car, that's not quite the case. So the goal of looking at this particular example of how you recycle different types of polymers, so that includes different types of plastics, of course it includes tires, but we've also got to be mindful that plastics come with a whole lot of additives that are introduced, for example, for UV stability. How do you actually account for the fact that there's titania, TiO2 for instance, present? Do we see that as a negative? Or indeed, do we see that as an opportunity? So what we have done at the Smart Centre at UNSW Australia is we've actually seen all of this as an enormous opportunity for us to recognize that a lot of these elements that are present, for example, in waste, actually present significantly higher order in terms of their value. And that's really the core of our understanding in terms of how we convert these difficult materials into high-value products. So green manufacturing as a philosophy is not just about the fact that you've got to be creating environmentally sustainable solutions. That's a tick, that's a no-brainer. You've got to absolutely do that. The other critical question to go with it is how is it going to be economically viable? Is that going to result in new business opportunities? And I think that's really where the question lies. Can we actually create new products and therefore new business opportunities, and therefore ultimately deliver solutions that are going to make sense truly in a long term? So if we're talking about circular economy and we're talking about how we actually use these types of end-of-life products, we need to be mindful of the fact that all types of solutions have to ultimately be economically viable. And that's really the core of what we are trying to do here. From our perspective, our industry partners, in this instance, One Steel, took enormous effort in developing this partnership with us, as in supporting students, supporting R&D to be able to deliver this as an example of not only the technology of green manufacturing with relevance to recycling polymers and steelmaking viable in Australia, but our technology is now also running in many parts of the world, like in South Korea at Seltzer Nordic as well, and UK and so on. So as I said, these are the challenges of recycling waste materials. We do need to have fundamental science. It is not good enough to rely on the fact that the polymer chemists are going to give us solutions under steelmaking conditions. That's not necessarily going to happen, because when we talk about using it in steelmaking conditions, we've got to remember temperatures are much hotter than what you would expect polymer scientists to be working at. We're looking at molecular transformation of waste materials at temperatures well beyond 1,000 degrees Celsius. So that's really where our understanding at the fundamental level has to come in. New opportunities and therefore lots and lots of new scope. This is really just one example. The complexity that these types of materials offer. I'm sure you've stared at the screen long enough and you obviously have realized what you're looking at. Tires, that's right. Even something as basic as a tire is not a mono material. You've got different types of materials that are present in it. So it's important to recognize at that molecular level, is there any reason why we shouldn't be looking at the presence of elements like carbon and hydrogen, and asking why aren't we looking at those two as an opportunity? And that's exactly what we've done in this particular study, is we've shown that the presence of high levels of hydrogen, which actually allows to release hydrogen molecules, nice clean hydrogen molecules into the process of electric arc furnace steelmaking, is one of the reasons why we've seen the kinds of benefits. So as I said, an automotive waste is anything but a simple sort of presence of a few different plastics. After you've actually shredded down a car, you've recycled steel, you're left with of the order of around 100 to 200 kilograms of the weight of a car, which is a complex mixture. And as I said, we've got to recognize it's not just about the plastics, it's the fact that you've got a whole range of other impurities. These other elements, of course, could be things like titanium, as I mentioned. They could also be things like silicon, which of course is present in silica in the laminated glass products. So I'm not going to run through some of these stats, but of course we do realize that traditionally recycling different types of plastics can be quite variable depending on, of course, where you are in the world. And of course, it's not just about our day-to-day products. These are rather simple in nature, and you might argue, well, of course, if you've got a nice simple stream of plastics, for instance, you should be recycling it back as plastic. Of course you should be recycling it back as plastic. We are certainly not advocating that you stop doing the conventional recycling. You have to keep on with the fact that converting waste materials as much as possible back into the original form has got some merit, and that's certainly one way to reduce our carbon emissions and to be able to save on energy. But the important point that you probably have picked up here is the fact that, again, a very rich source of hydrogen, 15% hydrogen, for example, in high-density polyethylene. And then the list goes on and on. You've got a whole range of other types of polymeric materials. As I was saying earlier, even something as basic as a tire that you might think is a simple product is far from it. Combination of different types of rubber, for instance, and of course carbon black, as you know. So lots and lots of good, highly valuable elements. Again, here's something like polycarbonate. Extremely popular in terms of its applications, a rich source of carbon, hydrogen, and oxygen. Pick up on one example, something like polycarbonate, for instance. Even something like this actually will result in huge amount of waste that might end up in landfills. So the question is, why aren't we looking at these types of materials and products as basically sources of these different elements? With polycarbonate, for instance, what we have shown is that at high temperatures, and we started with something as simple as your humble CDs, lots of waste CDs entering landfill, for instance, because of course people don't use quite as much for music, for instance. You can actually show that the carbon that you generate is such enormous purity and highly ordered crystalline carbon that you can indeed do a fantastic job in using that, for instance, as a replacement for graphite. So you can start to see the connectivity between traditional resources and recognizing what opportunities exist with end-of-life products. Now, I'm not going to get into the details. Again, as I said, a lot of this work has already been published. It's really about making the point that we do need to be able to understand the basic science and then move forward in terms of what it's telling us. What this graph is actually showing you, this picture is showing you, is that if you actually look at the top layer, which is basically liquid slag sitting in contact with coke, traditional metallurgical coke that is used in electric arc furnaces in many parts of the world, and for that matter, there might be other conventional carbons that might be used. If you now look at what happens to the ability of this liquid slag to continue to sustain the foam, what these pictures are actually showing, and time permitting I might play a video too, but what these pictures are basically showing is that the slag volume is actually decreasing. So we do know that if we are to sustain energy efficiencies and in general furnace efficiencies for an EAF, we need to be able to sustain that slag foaming. But the minute you actually introduce polymeric materials, we've shown some examples there, you can see the contrast. HDPE, rubber, PET, all of these different types of blended mixes that were used as carbon inject materials, so that's for purposes of slag foaming. What you actually see is that the performance of that foam, in fact, gets better and better. Now, all of this, of course, lab studies that have been tested and trialed and implemented on commercial scale furnaces. One Steel in Sydney and in Melbourne has been operating and using this polymer injection technology for many years. Again, lots of their numbers on a commercial scale are available in the public domain. Similarly, we've seen improved performance on other furnaces as well worldwide when we have introduced rubber as part of the mix. And of course, a large part of it is to recognize the fact, as I said earlier, that the presence of nice, clean hydrogen molecule is a fantastic opportunity for us to sustain that foaming performance. So look, what I'll try and do is I'll try and play these videos just for a short time because I do realize that time is of essence. What you're looking at here is straight down a high temperature furnace. You've got basically slag that's from EAF. About 30% iron oxide. It's sitting on a substrate which is effectively 100% coke, so traditional coke, and we've done our experiments where we always start off with the reference of what the traditional material that a company is using, for instance. So what you'll see here, of course, is as the reaction starts to happen at high temperatures of 1550 degrees Celsius, iron oxide reacts with that carbon, and of course, as you would expect, the reduction of FeO begins, and you've then got the ability of that slag to, for some period of time, sustain that forming, although not too long. Now, compare that with the next video, and I'll just play that real quickly as well. This is the one where we've blended in. So same experiment. The substrate has now got a blend of rubber tires. We've now got same slag at 1550 degrees Celsius. The reaction as it's starting to happen that you can see there is quite different to the previous case. And what I mean by that is you can actually start to see visually how that slag foam is indeed growing with time. And of course, what that is indicative of is that the gas bubbles that are being generated as a result of these high temperature reactions are actually being sustained inside the slag foam. So if you look at it carefully, you will see indeed, of course, that bubbling action going on, slag, the gas bubbles being generated, and of course, they're able to be sustained within the slag, therefore giving the kinds of benefits that you would expect a good slag forming to actually deliver in commercial furnaces. And that's exactly what we have seen, that in commercially operating furnaces, we see better performance when we've actually used a blend of rubber and coke as an inject material into our furnaces. Now, of course, as I showed before, the presence of hydrogen molecules, very efficient, allowing us, of course, to see these kinds of benefits. So that's really ultimately the critical question. If we start to recognize these types of new opportunities, we can do so much more with our manufacturing processes. I'll just take only a moment to show you some of these results that we've obtained in the labs. You can see on the graph that you've got metallurgical coke, which is indicative with that black line, and you've got basically a blend of rubber and coke as shown with the red, and that's just basically showing how the volume, when you actually use a rubber blend, is actually maintaining itself at a much higher level, and that's exactly what we see in terms of our furnace performance. As I said, a lot of the scientific work which actually shows you microstructure of the slag at high temperatures, and you can see those bubbles over a period of time, which is basically those dark, gas bubbles inside are being trapped in over a period of time, showing good performance. So look, I mean, we've talked about why we need innovation in this space. What exactly are we trying to achieve with green manufacturing? One of the things we want to be able to do is we want to be able to convert waste into value. It's no point saying we're recycling something and you make a new product and that product ends up in landfill after 2 months. So that's the important message here. It's not about the downcycling and just kind of doing recycling for the feel-good of it. It's important that we, as material scientists, as engineers, produce indeed high-value products that, of course, help society with recycling, help meet the needs of society, and, of course, importantly, the affordability criteria. If you can actually make a lot of these products, high-performing products, affordable, because the resources that we're talking about here, if you can actually use these waste plastics, for instance, that we're talking about, you can actually start to tap into that expensive titanium, for instance, that's present in titania, in the form of titania TiO2 in these types of materials. So that's the important point. How do you then create new opportunities, new product opportunities by converting waste into value? So essentially, it's going a little bit beyond the conventional recycling. It's really starting to ask the question, can we actually reform these complex mixtures of waste? Now, again, look, I apologize, but there is a lot of scientific information in here, and I'm going to skip through some of that, just to sort of make the point that a lot of work has gone into optimizing those blends. It's not as if you can continue to increase the amount of a mono material like rubber and continue to see improved performance. You need to be able to go back and have the right kind of blends and right proportions depending on the parent material. Here's an example. You can see we introduced polypropylene in the blend and compared that to rubber. Now the polypropylene blend still shows better performance compared to the black line, which is metallurgical coke, but certainly you can see that polypropylene doesn't perform as well as the rubber blend does. And again, that is attributed to the fact that you've got far too much gas coming out from the system far too quickly. So if it's not doing such a good job with respect to slag forming, well, let's start to look at what else can we do with it. So where else do we have PP? Polypropylene is present in a big way in the auto waste that I was referring to earlier. So you'll see XRD patterns here. You start to see that it's very easy to recognize and use the standard tool to be able to recognize, for instance, the presence of polypropylene. You can, of course, see what happens after heat treatment, and, of course, the comparison couldn't be more starkly different. You can see that before heat treatment, polymers all intact. You've got TiO2, as I mentioned earlier, in this particular mix. You can see after heat treatment at 1550 that we've transformed these into titanium nitride, silicon carbide, and of course, all of these are highly expensive, high-performing materials. Again, a lot of work on Raman imaging that we've done here, and you can see again, not only that you've identified TIN, for instance, SiC, you've also shown that the carbon that's being produced is highly ordered in nature. So lots and lots of new opportunities to explore.
Professor, I have to ask you to complete your presentation.
Okay. So what we are looking at here is just basically indication of how these nanoceramics are in fact being generated out of these different types of products. So look, I'm going to skip through some of this and really just finish off towards the end by showing you one or two videos. There's information, as I said, in the literature around where the implementation of polymer injection technology has happened. As I said, it's been implemented in places like South Korea, in CELSA in UK and Norway. I'm going to just probably finish off with a couple of these quick videos. These are confocal observations, again at 1550 degrees Celsius. And in this particular instance, we've brought in coke close to the slag, and you can see these massive bubbles, gas bubbles that are exploding, and that again is confirming the behavior and the manner in which, of course, slag reacts with coke. In contrast, if you actually go back and see the difference now, and I'll play exactly the same video, when we brought rubber in contact with the same slag, and you can see that you now no longer have those massive explosions of gas bubbles. You can actually see the dark particles are basically rubber particles interacting with slag, and where the rubber particles are interacting with slag, you can start to see these really minute bubbles that are coming out, of course, from as a result of these high temperature transformations. So again, it's an indication that for us, we don't have to necessarily see end-of-life waste materials as waste, but rather as new resources. The question lies, what are they capable of being transformed into? And if we can indeed convert them into high-value products, then it's certainly creating brand new opportunities, whether that happens to be using them as raw material for purposes of manufacturing steel, or indeed whether we're taking the waste that comes with steel products and transforming them into some other highly innovative products, like I was mentioning here around the nanoceramics, where you can use a combination of different types of waste materials and the associated mixtures. So I guess just to finish off the point that through this type of recycling science, we certainly have shown lots and lots of good opportunities are possible for industry. We, of course, know that waste is only going to get more complex. We've focused our attention here on cars. But you could make the same argument for electronic devices, extremely complicated, but also effectively providing lots of new solutions at the micro and nano level to transform them into highly valued products. So in a sense, it really calls for going beyond the 3 R's. The reduce, reuse, recycle are the 3 obvious R's that we're all familiar with. It really calls for a 4th R that really talks about reform, and it's about the transformation of these complex mixed waste streams that we have to deal with in a circular economy question. And of course, ultimately, how do you indeed produce these value-added green materials is the ultimate question if we are to achieve true sustainability. So thank you very much for this opportunity to speak here today. Thank you.
Thank you. So we have time for some short questions, so let's keep it to the point, please.
Excellent presentation, Veena. Thank you very much. I have a small curiosity. Has this already been tried in pilot level or in industrial level? Maybe in your industrial partner OneSteel, or it is not yet done?
So as I mentioned in my talk, it's been running commercially for many years. It's running commercially in Sydney, in Melbourne, so those are the plants that OneSteel has. But we've also been running commercially in other parts of the world, so I put up some examples of the kinds of places like Celsa Group, for instance. So it's UK, Norway, Thailand, CRB Steel in South Korea. So yes, it's been running commercially. And a lot of this data that I've mentioned in there is actually available in the public domain.
Okay. And another actually question is, what is the percentage of adding the replacement materials?
So I suppose it's probably reasonable to say that there's no such thing as a one single magic bullet that you can say, right,
true.
you know, you put this in and this is what you'll get. As you saw from a lot of the understanding that we have developed, it really does come down to a specific operation. So if you have a certain type of slag, for instance, it depends on the properties of slag. I obviously didn't get into the details. So depending on the iron oxide, the slag basicity, a lot of these factors that are well established in the literature about the role that, for instance, slag chemistry plays in controlling this performance. So you have to really look at it in a much more holistic manner.
Okay.
Ultimately, if you are introducing a new resource into a process, you got to understand the holistic impact on the overall process and really design and tailor that according to what you want to achieve.
And I have a small curiosity on the experimental way, because I think you have made the drop shape analysis in a normal tube furnace with a camera fitted on one side.
Yeah.
And our experiences were when a particular system is generating carbon monoxide, if you're using platinum thermocouples, it is devastating because of the carbon monoxide poisoning. And how do you take care of such massive carbon monoxide generation with your experimental setup?
Yeah, so our controlled thermocouple is not actually located inside the tube. You know,
Okay.
you have to be able to keep that away from your reacting system and ultimately do your calibration. When you're doing your measurements with a thermocouple that's located outside, you can do in fact your calibration to understand what the in-furnace operating temperature is going to be like.
Thank you.